Good morning, all of you. As we discussed in the last class, Introduction to Open Channel Flow. Today, I will continue Open Channel Flow, going slight bit more in depth about the Open Channel Flow. Looking that, I have been following now the best books for Open Channel Flow, which is the books on Hanif Chaudhary books, but it is a higher level book. But I can suggest you to read either FM White book or the Sindel Simbala book. So, most of the derivations we have taken from the Sindel Simbala book. So, we can really the correlated the discussions what we are doing it if you follow Sindel Simbala book. Let us discuss today what the contents we will go through for lectures. One very interesting things we will discuss about flow proud numbers and the wave speed, which is a new concept what we will introduce it. No doubt we already discussed about these mass conservation equations, linear momentum equations, energy conservation equations. These the equations we will apply for a control volume. So, it is a control volume concept what we discuss more with RTT, Reynolds transport theorems. So, that the thing concepts are used for the open channel flow to solve the flow depth, energy losses, the discharge, flow depth, energy losses, energy loss, and also we discuss about the discharge, all the variabilities things we discuss it in a open channel flow, maybe natural channels, maybe the man-made channels. One of the man-made channels, we India as a country, we are very much leader in constructing the canals. If you look at the history of the Ganga canals, you always can Google or look at the Wikipedias, what is the Ganga canals. The canal was constructed way back 1842 to 1854. So, it is about 12 years the constructions what had happened the Ganga canal. Today this canal is also functions, they are almost 170 years old. Canals also it is a functions, having the 33 megawatt power generations, 33 megawatt. Not only that, today's the our capital of the country, the Delhi, is getting about 240 million MLD, okay, liter per day for Delhi city. So, you can just understand it how we are the leader in open channel flow, how we are the best in the world constructing the canals. The one of the reputed institutes which earlier named as University of Roorkee, now IIT Roorkee, they were the leader, the world leader to construction of the canals. So, we have a inherently this knowledge about how to construct the canals, to understand about the rivers. So, the basic concept what I will talk about, it's not a new concept. So, that means if you look at the way back 1842 to 1854, we constructed the canals 170 years, still is running it and supplying it about 240 million MLD waters to potable waters to the Delhi city. That is what is happening it. So, if you look at that, we are leaders in the open channel flow as this is what was constructed for the as a navigation canals. Okay, that is what is as navigation canals. So, I am not going to more details how we were really the world leaders in these fields, because it is a very limited for you the open channel flow. I just want to tell you that when you constructed the Ganga canal, there was no computers, there is no hi-fi computing systems. The basic the conceptual idea they used to design canal systems, even if the alluvial canal systems. Okay, that's I am not going detail. So, if you look at that, that's all the experience what we have, and now what is the lifeline for Delhi city is the upper Ganga canals water feeding systems. So, looking that I am not going to more details, because as you know it, we have just a few lectures remain for the concept of open channel flow. So, more details is there if you have interested in next levels is the river engineering course and other courses are there. Now, if you look at that, just to think it that when you have let me have the river is flowing like this, okay, river is flowing, and this is what you have the bed level or the canals, this is the bed level, this is what you have the free surface, that is what you have the free surface, okay, having the flow depth of h, having the flow depth of h. If you have these things and if you create any disturbance, okay, let me there is a one big stone is there, okay, or just dump a stones here, it create a disturbance to these flow systems, okay, or you throw a stone to a river. So, it creates the disturbance. Once it creates the disturbance, how does it propagates it? Because there is a upstreams and the downstreams. Okay. Because of this disturbance, what is the wave speed? The speed of surface water wave. Okay, surface water wave. So, that means, if I put it a very simple way, this is what hypothetically we are creating a disturbance wave. Okay. If you consider is that there is a open channel flow is going on and we create a disturbance because by putting a stone. As you create a disturbance, that is what will be reflected on the surface. That means, we are talking about the surface disturbance, what is happening it. Does that disturbance propagates upstreams or it propagates both the directions in upstreams and downstreams, or it just propagates through to downstreams. That is what is indicates are the flow behaviors between different conditions, flow regimes. That is what we look at in terms of speed of the surface water wave, surface water wave. That is what is created by natural processes like the flood occurrence, lifting a gate, having any stones or bed roughness, all create the disturbance to that. When you create the disturbance of that, then we try to look at how that disturbance is propagated. What is the speed of the propagations of this surface wave? Let be designated as C naught. So, what that speed? See, if you look at that as we discussed earlier, we talk about three types of the flow: subcritical, critical and supercritical. In terms of the flow Proud numbers, we define as if a lesser than 1, that means the gravity force is more than the inertia forces. With this the case we define as subcritical flow. Okay. When we have a very rare occurs it that we will have the inertia force is equal to the gravity forces of the flow systems, that we call the critical flow. If a flow Proud numbers is greater than 1, we call supercritical flow. As the equations is a part of inertia forces and by gravity forces, you can just rewrite this, okay, from you can find out the flow Proud numbers is a functions of v by square root of g y. Here the characteristic length is the flow depth. Okay. So, now if you look at that the flow Proud numbers, what we define it as a inertia force by the gravity forces, and when you do this inertia forces gravity forces, we are getting the flow Proud numbers is a functions of the speed of water. Okay. That is what again I need to write it this that what I am getting is this flow Proud numbers, okay, as the speed of waters divided by g by y. Many they define it, or I will also derive it. This is the speed of waters, speed of water divided by the speed of water wave, or any liquid we can consider it is a water wave. That means, this is one speed which is equal to the C naught, is equal to the C naught. That is what we are going to derive it. So, we will talk about at the low velocity the flow Proud number lesser than that, small disturbance travels upstreams, affects the upstreams conditions. At the high velocity, when flow Proud number get small difference cannot travel the upstreams, thus the upstream conditions cannot be influenced by the downstream conditions. That is what I try to explain to you, looking these figures and with a disturbance, why does happens it between the flow parts, the dominancy part of the inertia forces or the gravity force components. So, definitions of the flow Proud numbers, the speed of the velocity by the speed of the water wave. So, velocity by the speed of water wave. Okay. So, now the point is coming it how to derive the speed of water wave. Okay. How do derive the speed of water wave, which is a functions of the flow depth. It is a very simple things, as I will talk about. As another disturbance, you consider it that you have the I am just resketching these figures. You have the river and you have a gate. Okay. So, you have gate and you are just lowering the gate, and after that you keep it the gate positions here. So, definitely in upstreams you will have a flow like this, then there will be a energy dissipations like this. So, these the reasons we will have a flow Proud numbers lesser than 1 is the subcritical flow. Here you will have a supercritical flow, then you will have a subcritical flow. So, if you look at that same thing, this is a subcritical flow, supercritical channel. In betweens, whenever a convergence of flow happens from the supercritical to subcritical flow, there will be a formations of the eddies, and there are a lot of energy dissipations will happen. There energy loss will happen. The turbulence formations you can see it just downstream of a dam structures, you can see the turbulence because of the formations of hydraulic jump. Okay. This is what called its hydraulic jump, and we try to design a hydraulic jump because at these hydraulic jumps the mixing process, the aerations process happens very dominantly. No doubt there is energy losses happens it, which is required for some of the cases, but the hydraulic jumps which is created from the supercritical flow to subcritical flow at the transition zones, which makes the sound noise, it makes the turbulent structures. Because of that, you can have a significant energy losses, and those regions there's jump formations are happening. That's the reasons we define as a hydraulic jumps. Some of the times we believe we need a hydraulic jumps for mixing this chemical process, chemical things or erosion process. All we need a hydraulic jumps for the formation. So, we will discuss more about the hydraulic jumps. Now, if you commit that the speed of the surface wave, as I take it very simple way, that let here have a flat channels, okay, and I have the depth of the flow is there, and I just make a piston here. Okay. So, there is a piston here, and this piston is moving it, let me del V, and this is the fluid at the rest having let me y depth, and this is what the surface wave having a depth of delta y, and it is moving with velocity c naught, that is the speed of water wave, that is the speed of water wave. Okay. So, as equivalent one piston is moving it to creating a surface wave of height of delta y, it is a smaller, and the speed will be the c naught value. We need to quantify it, how much the c naught values. So, what we can do it, we can have the same concept, we can use of control volume, the same concept and the certain assumptions, okay, no doubt about that. So, we will have the assumptions, we will have make this the control volume. So, basically I am making this is my control volume, this is my control volume. If this is my control volume, if I just zoom it, the control volume part, I have the control volumes like this, the bottom shear stress acting is could be much lesser than other force component, okay, much lesser than other force components. Because of the bottom shear stress what is acting on this on this channel, that will be much lesser as compared to the force acting. One is pressure force. So, here we can assume it that pressure distribution is hydrostatic pressure distributions, okay, hydrostatic pressure distributions. So, you can assume it, and that is quite this assumption is quite valid to have this is the y depth as it is a, and this is the depth of y plus delta y, and this is what is moving with c naught, okay, it is moving with the c naught. As it is moving with the c naught, we can always have the velocity, just you can see it as a moving control volume concept, okay, as the shear stress is there. So, you can see that it is just a reverse, like you know it, this will be moving with c naught, but this is what will be having this moving with just c naught delta v, okay. This is the velocity, okay, and we can assume it because this fluid at the rest, and this is the zones which is moving on the delta v. So, if you look at that, if this is the control volume moving it at the free surface, it looks like that, it is a negative direction, so it will act it as you can see this part, and these two velocity distributions help us to crossing the mass fluxes as well as the momentum fluxes. What are the force components are there? If I am looking it, this is the x directions and the y directions. So, I have the two equations with me. One is mass conservation equations for this control volume, another is I will apply the linear momentum equations in y direction, because I do not bother about the x directions, will apply not in the y directions, because that is not necessary for me. So, I am looking the x director momentum equations. From this I can find out what would be the relationship between the speed of water wave and the flow depth. That is what we are looking at. Now, if you look it as it has given it, the first component assumptions is very nearly constant. So, that is what is assumptions, we many of the times we did it, and beta 2 is closer to unit, which is the momentum flux correction factors. Distance of across the wave is a short, the frictions at the bottom surface or air drag at the top surface will be negligible quantity. That is what I discussed it here. The force due to the frictions at the bottoms will be much lesser than the hydrostatic pressure distribution force what we are getting it. And the pressure distributions can consider it as a fluid at the rest. We can estimate it, what is the pressures at this point, the rho g average of height, that is what will be the rho g to y, the average will be the half of this, and same way this average pressures you will get it in y flush delta. So, this is y flush delta. The pressure at this will be rho g y, that is what you know it. And what is the mass flux are coming it? We can put it, the mass flux what is coming it as a rho c naught y b, that is what is mass flux is coming it. And if you are looking the horizontal directions equations and you are equating it, the first is the steady mass balance equations for this control volume, again we have sketched it. So, if you look at that the control volumes, and as we are telling it as I explained it, the same concepts are there with how the velocity becomes negative components and all. So, if I apply this mass conservation equations, I will get a relationship with this the velocity c naught delta y, y flush delta y. This is very simple concept what we discuss as a integral approach. The same way in the x directions, I will apply the sum of the force is equal to out beta times of momentum flux, which is going out from this is equal minus of beta in. This is what we discussed much earlier, but just we substitute the force component as we did it here, as we did it. If we substitute it, we will get a long expressions like this, and finally, we get a relationship between again I can write it, the c naught, the speed of surface waves is square of g y 1 plus just some rearranging the terms and 1 plus 2 y 2 y. Now, if you look at these terms, since we are considered it, most of the times we will have this surface wave height which much lesser than the depth of the water. So, in that case these terms is become close to the 1 value. That means, the c naught, the speed of surface wave is equal to g times of y. g times of y square root of that. So, it can have a positive and negative. More details I am not going it, but again we are coming back to this. The flow proud numbers is, again I am writing it, not only inertia forces by gravity forces, it is also the velocity divided by the speed of surface wave. Okay. That is the definitions, the new definitions for flow proud numbers. So, if I have a velocity speed of surface wave larger than the velocity, so we will have the subcritical flow. If the velocity is larger than the speed of surface wave, then we will have a supercritical flow. So, just like we talk about subsonic, supersonic, sonic speed. So, same way here in case of incompressible flow, the free surface flow, we talk about speed of surface wave with respect to the velocity of flow. If the velocity flow is larger than this, then your flow proud numbers will be greater than 1, the flow behaviors will be the supercritical flow. So, if you create any sort of disturbance, it will not propagate to upstreams, it will go to downstream. If the conditions when this velocity is lesser than speed of the surface water wave, which we have derived is a function of the flow depth, square root of the flow depth, that times we have subcritical flow. The critical flow is the condition, there is very special conditions where the velocity is equal to the speed of surface wave. So, that way you try to understand it, there is a physics behind that to classify the flow, except very simple way to define the inertia force by gravity forces, but in terms of the open channel flow where the speed of the surface wave is matters to us, we try to look at the ratio between the velocity and the speed of the surface wave. More detailed derivations you can look it here in Sindel Simbala books, or you can look at FM White book. I am not doing the line by derivations, but try to understand this physics of these problems. Now, if you look at as I said it, we follow the basic, the integral approach concept, the average conditions. Okay, we are not looking at detailed flow field like as we discussed for differential analysis part. So, when you talk about, because when you design the open channel flow, we may neglect it, the velocity distributions, how it is happening it, how these turbulent structures are creating it. So, those if I are not considering it, and if I know it is what is average velocity, what is the energy losses and what the flow depth, then I think this one dimensional equations, okay, which we already derived, which is Bernoullis equations, for that what we can use it, which talks about the total head is equal to, you know it, okay, b square by 2g, the velocity head, the depth, okay, which is talking about your pressure head, that is what is the pressure head, and this is the elevations head, that is the pressure head, we make it as a rho g h. So, that is the reasons we can get it the pressure head components. So, this is what the total energy. As I discussed many times that when you talk about the rivers, we take it river, the lines whatever is this is the x directions, and this is what we consider the datum. That means, we are considering very flat terrains, okay, very flat terrain. That is what it happens when you construct a canals, you cannot the slopes are very negligible. So, it is order of 1:10,000, 1:50,000. So, that way the scale that is the z variations we can consider is negligible is that. So, if is that we introduce for very specific cases of open channel flow, we can solve with a two heads. One is the pressure head, which is we define as y, and other is the velocity head. Okay. And this energy, as we have with a certain assumptions we have commit to this, we define this energy of specific energy, which considers the head, as we discuss about that energy per unit weight. So, this is the pressure head, this is the velocity head. So, we are not considering the potential head or the head above the datums. So, if you have you can consider the new simple way we can analyze the flow field using a specific energy concept, which is having a two component of velocity head and the pressure head. Now, if you look it as we did it for the in case of the pipe flow, we can apply it the same concept, like I have a channel and I have this free surface, which is the hydraulic gradient line. I have this energy gradient lines. Okay. So, if is that conditions, if I consider the two sections, section 1 and sections 2, okay, and if I draw a line here, this is what my energy loss. This is what the energy loss H L as we define in the pipe flow. Okay, we did it the same things. Okay. So, we can have write for the two sections as similar to that, the Z 1 plus H 1, okay, B 1 square to G is equal to Z 2 Y 2 B 2 square 2 G plus energy loss in terms of head, which is reflected here in the diagram. This is the part what we have the energy loss. So, if you draw the energy gradient line, the free surface line is the hydraulic gradient lines, you can get it this component. So, if this Z 1 and Z 2 is very closer by, so you can write it the specific energy of E 1 is equal to specific energy E 2 plus energy loss. So, very simple things. It is very simple things as we learned from the Bernoullis equations, as we learned from the pipe flow, the same concept we are putting it with the assumptions is that these are no doubt, as I said it, very flat conditions. When you construct a canal, when you constructed the natural rivers are very flat, okay, except in some of the waterfalls and all. So, you will have the energy losses, specific energy of E 1 and specific energy E 2, they have the relationship between is that E 1 at the sections 1 is equal to, which is the upstream sections, is will be the energy specific energy E 2 plus energy loss, okay, in terms of this. So, please have a the same concept what we discuss in pipe flow, we discuss about Bernoullis equations. Now, if you look at as I said it, when we constructed way back almost 200 years back, Ganga canals and all, we did not have opportunity like now we have a computing facilities and all. The people used to the specific energy curves to understand how the flow happens, how much of energy losses happening. It is a very simple, the graphic way graphically understands how the flow happens in a channel flow. So, people used to today we have so much computing facilities and we have empire. So, they used to have a very simple graphic techniques to solve the open channel flow, design the open channel flow. how they do it. Okay. Then let me I go for, as I said it, we are talking about open channel flow, where a channel when I am designing it. So, my Q is more or less a constant, like for example, is very close to the 300 meter cube per second as a design discharge for the Ganga canal. So, you can Google, okay, you can look at the Wikipedia. So, that is discharge which is in a canal is going it is more or less constant. If it is that, so when the canal is moving at 300 meter cube per seconds, then how they are having the relationship with energy versus the flow depth. Okay. It is a very simple graphical technique, but this graphical techniques gives a lot of knowledge about this open channel flow. So, if you draw, as you know it, the E is equal to y plus v square by 2g, and for a rectangular channels having the b is the width, y is the depth. So, you can have a v will be the q by a, that means it will be the q by b into y. So, you just substitute that once. If you just substitute it, what I will get it? I will get it E will be the y is a q is a constant here. So, q square is a constant is a for a constant flow. If I have a 2g b square is the width of channels into the y square, b is let be constants. So, it is a E is a function of y and the y square. If you just plot it, this is the E equal to y line, it is a 1:1 line, and if you draw this curve, okay, please practice this curve, okay, you will get like this. This is the nature of the curve. Okay. Nowadays, you have a lot of tools, mathematical tools are there for a particular discharge of q, the q constant. If I draw the relationship between varying the y and the E, I will get this curve. That is what here. This curve what is indicate for us? That for a particular discharge q, okay, there is a minimum energy, and with that is a representing a depth which is actually the critical depth. That derivations we can always do it. This is the minimum, beyond that the flow is not possible, it is a really impossible. Flow can happen for a q equal to the same constant discharge, because that is the minimum energy is necessary to have the flow. Minimum energy is necessary to have a flow, minimum specific energy is there for this constant discharge. So, if you look at that, and just you can see that this is the critical zone, this is what the critical zone, and it divides into two zones. One is supercritical and another is subcritical zone, and the line will be representing the critical flow zones. Okay. With a different discharge we will get it that. So, you have a supercritical and subcritical, it divide the zones, and you have a E minimum. The E minimum represents us the critical depth, and this line is a y, this line is v square by 2g. Okay. At the critical depth, whatever the velocity we also call the critical velocity. Okay. That is the equations when you have the flow problem numbers is equal to 1, inertia force is equal to the gravity force. The second definition is what we derive it, the velocity of the flow is equal to the speed of the surface wave, or at their locations if I throw a stone, it will not move any directions. The waves whatever created, it will not move it to any directions. So, if you look at that way, this critical zone, what I get it, it has the two components divided, is one is a subcritical, another is supercritical. But very interestingly, if you look at that, if I take a particular specific energy and take a line, that means I am getting a two depth y 1 and y 2. One depth, which is the higher depth where the velocity will go, that is the subcritical zones. The depth is a less, velocity is higher, the velocity is high, head is higher, that is the supercritical flow. So, you can understand it drawing this specific energy curve, that how the patterns of this curve, how a particular discharge for a constant discharge, how the variations between flow depth and the specific energy. That way we try to look it. Now, we are looking in very mathematical way, that we know it to estimate the E is a specific energy is a function of flow depth and the constant discharge is a constant. So, we can find out the minimum of these functions, which is very easy to do it. Okay. That is what the same things as I explaining it to channel width B, you can have a discharge per unit width and you can derive these equations, which is already I have taken it, or you can make it like this. Okay. So, it will be the constants for a particular discharge. Okay. That is what is given it here. But more interestingly, so if I look it at which point we will have this E minima, this point if you look it. So, there are the two sections and you can have a subcritical flow and also we can have a supercritical flow, we can have the critical depth. Okay. And this is the line 1:1 lines where the specific energy is equal to the flow depth. So, you have the two depths, that is what is called the alternate depths. So, the river or the open channels, it has a freedoms with the same energy, specific energy, it can flow through either a subcritical or the supercriticals. That is try to understand it with the same critical energy, specific energy, the same specific energy, the channel can flow either subcritical or the supercritical. It will have a two different depth, two different velocity. So, two different depth we call alternative depths. Okay. Alternate depths. Okay. So, alternate depths. Now, if you have to talk about how specific energy components are there, and again we are revisiting it. I think that is not a big issue, that specific energy curve, this is E minimum and you have a E value, you have a Y value. So, what you need it to get it this, you just differentiated specific energy with respect to Y. The point is 0, that what we give a relationship between Y c and these values. Okay. That is a critical depth. So, if I just differentiate it, making this is derivative is equal to the 0, I will get it again same things with a critical velocity and it will be satisfied it the flow Proud numbers is equal to 1, the critical, or the point of minimum specific energy is indeed the critical point where the flow becomes critical, the specific energy reaches to the minimum value. So, with this let I conclude today's lectures. Thank you.